Hello and welcome to Calculus 3. Welcome back. I don't know what I say. It's section 11.5, lines and curves in space. So we know about lines and curves in 2D. Some of those are called functions. So you have a line y equal mx plus b. You have x squared, that would be a curve. But also you have a circle with x squared plus y squared equal r squared. You have ellipse. So all of those were in 2D. They only contain x and a y. Now we are moving into 3D space, and we would like to come up with curves in the three-dimensional space. And you can think of very simple concepts like a chord. I knew there was an extra one. I can't pull it up. There we go. So we could possibly write the equation for this particular line in space. So we would like to figure out what would the equation for something like this be, and later learn how to come up with the integral that calculates the length of the curve, as we hold this to be a path for the particle, or maybe it's the mountain road, right, that wraps around the mountain. So we can find a use for something like that easily, but first we have to learn how to describe curves like that in space. So you are okay with those curves in 2D, because as I mentioned, those are the lines, functions like x squared and e to the x and so on. Now let's see how we deal with this in 3D. The concept that we are learning is called a vector-valued function. And the vector-valued function will have we are going to use notation R as a function of time, or a parameter t, and that one is going to be given as x of t, y of t, and z of t. So those are the components. Now you see that instead of having three numbers in a vector, you have three functions which ultimately generate numbers. So first we have to understand that the point, let's say 3, 4, 7, is a location in space. And then we understand that the vector 3, 4, 7 points to that location from the origin. That will be a vector. So the terminal point of that vector is 3, 4, 7. So there is a point, and then there is a vector. And the notation, whether it's parentheses or spiky brackets, will tell us whether it's a vector or a point. Now, x, y, z is supposed to generate not just 3, 4, 7 as a location or a vector, but anything else that is going to describe the entire curve. So I'm holding this piece of wire. This is just a USB cable that charges cell phones. And if you're looking at this, imagine in the corner of the classroom 0, 0, And then you have a vector which points towards the USB side plug over here, and that's your 3, 4, 7. Then you recompute at t equals 1 second. So how much or how far would the ant that's walking on this path, how far would the ant get in 1 second? So that would be t equals 1, would compute the next point, t equals 2, t equals 3, t equals 4, 5, 6, 7, along the line. And every time you plug in a value, or intermediate values like 1.5 or 1.7, you will be able to actually point by point trace the entire line from the beginning to the end. So in a 3D space, I have a 3D coordinate system with good old x, y, and z. I'm going to have some kind of a curve where from 0 to here is a vector r, and then you have the point P. And then I can draw another vector, and I'll call it r star. I don't want to use prime because that's reserved for derivative. R star, and that will give me P star. So the difference between the R and R star is the length and the direction, obviously, but they all evolve from the same vector R for different t's. So I don't have to use R and R star. I can just use R. Instead of R of t, I can say R of t1, R of t2, R of t3, t3, and so on, depending on the location where I am.
So t, you were just saying like for the amp and like time for seconds. T isn't time, right?
T could be understood as time.
Okay,
it's a parameter. Remember chapter 10, Calc 2, parametrization? So what you have here is a collection of 3 equations which describe the curve in respect to the common parameter t. So we are not defining it yet so strictly as a parametrization, but I'm telling you right now that is your set of 3 parametric equations from 10.1 right there, combined. Yes? P star, R star. But I could just call them R of t and then t1, t2, t3, depending on where you are in space. So I hope that you are going to understand this because it is an upgrade of what you know from your previous calculus life or pre-calculus life. So previously, let's say you had x squared, right? So for 1, you go and you get 1 back. For 2, you get 4, and so on. So your input was directly x and output was y. Now your input is t, and the output is the vector which ultimately gets you at the tip of the vector, the point which lives on that curve. So to give the simplest possible example of this, we're going to take a look at, let's say, vector r as t squared, t plus 1, and something. What else can I put? I ran out of ideas. I'll just put number 4. It's going to be, z is going to be 4 all the time. So if you look at this, you can compute the point at t equals to 1 as simply 1, 2, 4. You can calculate the vector at 4 as 16, 5, 4. You can compute for any value because These are all polynomials. They have no restriction in terms of domain or what you can plug in. So you can have anything. Guys, this is a function. T is the input, and the vector is the output. And that vector has the tip where the arrow is, and that's where the point is that you get to draw. So this is called a vector-valued function. It consists of three functions, one for x coordinate, one for y coordinate, and one for z coordinate. Yes? Well, the line in space that it's not bounded is infinite. So the same thing like how you, what do you do with this, right? Good. So you will have the same concept. Eventually, we are going to hit the limits and derivatives and integrals for these curves, because you will be able to find their length. You will be looking for the limit. You will be looking for the integral and other things. Awesome. Okay. So the next order of business is for us to start understanding the equations of these curves in space, and we are going to do the most fundamental one, which is a straight line. That's the first one we have to understand. So let's talk about linear line, straight line in space. So straight line, linear. So please, if you are looking to save me a lot of pain and stress and annoyance, make sure that your line, linear line, has only x, y, and z in it, because those are linear terms. You are not allowed to have squares and roots and sines and stuff like that. Linear line is y equal mx plus b in 2D. Single y, single x, no roots, no exponents, no exponentials, no trig. It's just x and a y. As soon as you have y equal x squared, it's no longer a linear line. It's quadratic now, right? And then you have cubic and so on. Calc 3, same thing. In Calc 3, we are going to have a linear line, and a linear line is only allowed to have t to the first power, x to the first power, y to the first power, and z to the first power. All of them have to be first power. So, yeah. Now let's see how that works in 3D space. So we have x, y, and z, and we would like to learn about the straight line, call it L, that goes infinitely, right? This is a skewed line, so it's not parallel to any of the surfaces, or it could be, but it's just a general line. And we are going to describe the line, again, using two concepts. If you remember your basic algebra, you know that all you need is a slope and a point. So in 2D, if you have a point somewhere and you know the slope, you will strike the line through that. So you have a point P and the line slope M equals to some value, and you will plug that in and get your y equal mx plus b. We cannot require anything more in Calc 3 now for a 3D line. You must still have the same idea. Some kind of 3D slope and a point through which the line is going to go. That's all you need. So we are going to have the point P0, and the point P0 is going to have the coordinates x0, y0, z0. So that's like our initial point. And then between P0 and P, we are going to have this vector. And that vector is vector V. We'll call it vector V, which is, I'll put that in quotes, 3D slope vector. Because that one determines the orientation, determines which way the line is going to go once you anchor P0 somewhere in space. And then obviously you will have these vectors that stretch towards those 2 points because everything is measured from origin. So now this point P is the general x, y, z. And if you carefully look at your vectors, R0 is definitely a vector, x0, y0, z0. And vector R must be x, y, z vector. How do I know that? I know that because the terminal points are x0, y0, z0, or x, y, z. Remember my the talk that I started the class with? Right here, you have a point, and then you have a vector from the origin that points towards that point. They have the same numbers. It's just one is a point, one is the vector. So now that I have P0 and P, which have the coordinates x0, y0, z0, and x, y, z, then the vectors that stretch to those points are R0 and R the way they are. Now, one more time to reinforce from last class, we learned to create a vector PQ, you go terminal minus initial. Well, terminal point is x, y, z, and initial point is 0, 0, 0, right? Every vector R starts at the origin, which is why they will always have the same, the point and the vector will look the same, except one has parentheses, one has bracket, the spiky brackets. So now that we have this idea, don't we know that y equals mx plus b? So y, which is in our case r, is equal to mx, which is v, and we know that the input is t, plus the initial point, which is r0. This is known as the vector equation for the line. In 3D. Well, actually, this is in any D. I'm going to erase this. This is in any D. This is a straight line. It's 17D if you want to. Because these are vectors. And the way you add dimension is you just add another variable. So if you have 17 letters in your alphabet, there you go. You're good to go. Now, we understand that vector R is x, y, z. So I'm going to first rewrite this as R0 plus VT. And then I'm just going to write it out. X equals x0 plus AT. Y equals y0 plus BT. And finally, Z equals Z0 plus CT. That's the parametric set. You do not get to break this and use one equation at a time. All of these have to be used at the same time. We also denote that vector v, which is the slope vector, right, quotation marks, is ABC. So this is the one that determines the steepness, the direction of your line. And then you also have the parameter t, which you can regard as time, which could be finite for line segments or infinite. I can't use the equal signs because I want to go from negative infinity to positive infinity, in this case, for infinite line. So this one is the parametrization . This one is the one that you will use most of the time to solve problems. Parametric equation of the line. Now, clearly, this is in 3D because we only have x, y, and z, so it is 3D. And that takes care of the line portion. Now, we can do a lot of cool stuff with this. We're going to do a whole bunch of examples now. But before we do that, I will note that you can solve each one of these for t, right? Because in the first one, you have x minus x0 over a, and that's equal to y minus y0 over b, which is equal to z minus z0 over c. Now, that equation is useful when you're computing certain problems. So this is just like a side note. That will pop up eventually, so keep that in mind. These are your equations, and then we can solve for parameter t, but you don't get to put it into one equation. You still have three-sided equality, right? This equation has three sides. So that one would eliminate parameter t. It eliminates parameter t, and you only have the points that are actually visible on the piece of paper. And now the moment that you're all waiting for, you doing problems, right? So let's start with write the equation of the line. With Teotl. You never heard of Teotl before? Write the equation of the line with Teotl. True? No, it's not Serbian. We don't have W in Serbian. It's an unnecessary letter. So write the equation of the line through 3, negative 7, 5 with vector 2, 1, negative 8 as a slope. You cannot get anything easier in Calculus 3. Well, actually, yes, you can actually add two vectors. That's easier than this. But this should be the cheapest problem, right? You have equation, you have the point, plug the stuff in, What is this 3, negative 7, 5? Initial point. So that's your zeros.
Yes, but you have to wait for the break. In like an hour, less than. We finish this section and then there is a break. It's 10 left.
No, the swimming left for an hour.
Exactly.
He doesn't do it.
Bye.
Bye, see you later.
So I hope you guys had this solution. It's only 15 seconds to plug it in and you're done. Now, the next problem is much more interesting because we are going to again write the equation of the line given negative 1, 3, 5 and 3, 4, minus 1. So I'm giving you 2 points in space and you get to write the equation of the line that goes through those 2 points. Now think about the method you used in basic algebra to find the equation of the line given 2 points, and use the same method here. It's the same steps, it just looks a little bit different, but same steps.
Wasn't Serbia part of Yugoslavia?
Very good. Even for five. Okay, so when you have 2 points in your algebra class, you used y minus y1, x minus x1, created a slope, and then you used one of the 2 points to create the equation, right? Well, now you are going to use 2 points that you have on the line. So if this is the line that you're looking for, and then you have these 2 points, call them A and B. Do you see how A and B create a vector AB? And wouldn't that be your good old V pal, right? So by simply subtracting, so you don't even have to do the slope thing with division. This is how much Calc 3 is easier than your previous math, right? You get your vector V by simply subtracting. So 3 minus negative 1 is 4. 4 minus 3 is 1. Negative 1 minus negative 6. And there is your vector V. And you have your initial point from where the V starts, which is A. You have to be a little bit careful about that. And you just write out the equation. X, Y, Z. Negative 1, 3, 5. Plus 4t plus t minus 6t. Done deal. Here's your initial point A. Here's your vector V. Here's your t. This A is your good old R0. You can't miss this stuff. This is your answer. You should include that t goes, because it's a parametric set, you have to define the t. It's a disgusting bracket. Now, you can also write this as a vector valued function, because we know straight lines are functions. And you can write it as negative 1 plus 4t, comma. There we go. So now it's clear that this set is the parametric set of equations. It's clear that our vector R, the vector valued function, is just a collection of those functions, which is collection of parametric equations, which is the stuff that you learned in chapter 10 when you learned parametrization, 10.1. If you haven't learned that, well, you're doomed. You still have time to learn, but and now it's the time for us to take a look at the line segment. So I want to find the line segment let's go with problem 28 from textbook. Line segment joining -1, -8, 4, and -9, 5, -3. So line segment is just a finite piece of a line, right? So what should be different than the previous problem? Do we do the same thing? We do the same thing, right? Except now, this condition will not be there. You are going to have maybe, I don't know, from 5 to 8 or from -1 to 7. You are going to have values for t which would create line segments stretching between these points. So you will have to figure that in addition. So vector v is immediately what? So -9 plus 1 is -8. 5 plus 8 is 13. -3 minus is -7. And we immediately have our equation of the line, which has -1, -8, and 4. Okay, so now let's be smart about this and figure out what are those values that we have to have here for t. Well, what has to be the value t so that this line segment, when you plug that value t across the board, gives us the first point? 0. Because as you put t equals 0 everywhere, it returns the initial point. So that should be common sense. So t starts at 0. So t starts at 0, nice. And now we have to get -9. How do I get -9? If t is equal to 1. Now obviously not every problem is going to be 0 to 1. Some problems are going to be 1 to 5. Some problems are going to be 0 to 7. you can either go from -2 to 5, depending on what, which way these things work together. Yes.
Is one of these less than or equal to, while the other one like -infinity?
Good question. So the question was why in this case we have equal signs as well, and in the previous problem we did not have. Well, we cannot include infinity. So you never put less than equal to or the bracket, which is the closed set with infinities. Where right now the endpoints are included, for the infinite line, there is no endpoint to use less than equal to. So when you have the entire line, you have to put just less than when you use infinities. And for the line segment, which is a finite piece which includes the endpoints, you will use less than equal to. Cool question. Thank you. So I hope you will learn, memorize the equation of the line. And now we are moving on to the next part, which is curves in space. So you all saw me, right, hold that wire. This will have an equation. So if I'm not moving it, if it's fixed in space, it has its equation, because that equation would be the path for a particle to move in space, right? A piece of dust that it's carried by wind takes this path, or ant walks on this path, on this wire. So we do have a way to describe that. Also take the mountain road, right? So erase the mountain, erase everything, and just somehow suspend that road in space, in nothingness. So there's just asphalt, right? And then there's a car that drives on it. So now you see that road is our vector valued function r, and then by figuring out derivatives and things, you will have the velocities and acceleration and all of that good stuff that you learn, because you conquered all of that in your 2D realm. Now it's the time to do the same for the 3D. So it's the acceleration of the end and the velocity of the end. And the velocity is a vector whose magnitude is speed, right? So all of those cool things that we can discuss now that we know how to write these 3D functions. So curves in space, we are going to, again, we're going to start with r of t is f of t, g of t, h of t, three functions which generate the vectors, which generate the endpoints, which point by point creates the line. We can also understand this using the IJK notation. Don't forget to put the hats, those are unit vectors. See you next week.
No, come back.
So we can use that notation as well. Orientation of the curve is positive in the direction of increasing t. Those of you who took my Calc 2 final, you know that this was on the final, this particular statement. This is covered in 10.1, orientation of parametric equations. So if you have, let's do the simplest possible example, which is circle in 2D, right? So you have a circle, x equals 3 cosine t, theta, t, it's fine, and y equals 3 sine t. So this is equation for a circle with radius 3. That's a little review. You should know this. What you might forgot is that the orientation is counterclockwise. We do have x and a y, which is 2 degrees of freedom, but then we also have t, which gives us extra degree of freedom, and it manifests itself as the orientation, which way the motion goes. So in this case, you can quickly figure out that this is correct by simply computing just two values. Compute t equals 0. When t is equal to 0, x is equal to 3, and y is equal to 0. So this point here is t equals 0. Now we're going to compute t equals pi over 2. T equals pi over 2 is x equals 0, y equals 3. Now that's the pi over 2. You clearly see that the motion for the line starts on the x-axis 3, and then the next one is here, and if you compute, the next one will be there. So you see how the motion is counterclockwise. Now, if you are to swap sine and cosine, you will still have the same circle, except now motion will be clockwise. So if you are to swap the sine and cosine, you still get the same circle, except the motion would be, the orientation would be clockwise. So orientation of these curves is in the direction of increasing t. As you go from 0 to 1 to 2 to 3, or from 0 to pi over 2 to pi to 3 pi over 2, 2 pi, and so on. And now we are going to discuss one of the coolest shapes, and that would be the helix. So the helix looks like a spring. So those of you who are into engineering, graphics, and so on, you would call this side view. Because and you would have a top view, which is just a circle. But when you look from the top, you only see the circle, and you see the circle towards the XY plane. Z is poking into your face from the page as you're looking at it, right? This is the top view. So now, here are some of the, what I consider common sense, but then if you're not visual, you might not. So I'll kind of back off a little bit on that comment. When I look at X and Y components of the helix there, I see a circle. So I'm going to write, if these are 3's, right, there will be 3's on this thing as well. If these are 3's, I would write 3 cosine t, 3 sine t, and that covers x and y dimension, which is the base, because that's all I see from the top view. I see the circle. And now, when I look from the side, I see a constant rise. So I'm going to call that just t. It's rising. I could compress this into a disk and just have 3 cosine t, 3 sine t, and then say at the elevation 2, let's say, if I just put instead of t, if I put 2, then all of it becomes just like a coin. There is no verticality to it, because the z component, which is the one that stretches it away from the circle into the 3D, is a constant. It's not function that evolves. I can make this grow faster, grow much faster, right? So how fast this helix is going to progress depends on which function I use on z, which is the one that stretches everything up. So I'm not sure how well of a graph I can make, but thinking about this, if I want to start here, it's going to go, because exponential functions, they're lazy, 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 bam, right? That's what exponential functions do. So that's what happened there, right? Lazy, 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 and then explodes up. It is still going to curve around, but you have to wait a long time before it makes the full loop, right? Because it's exponential, it grows quickly. So the helix is a combination of a circle and then the growth. Another thing that was, when I took Calc 3, was immediately common sense to me, was that the 2 dimensions which create the circle were x and a y, and I see the sine and cosine in x and y spots. But there is no reason not to think about helix also being maybe horizontal along either x or y axis, right? So as a student, I used to call that dimension a special one, right? Because I used to call z, in this case, special, because x and y together give me a circle, so they're like a pair, and z is the one that is different. And we'll see this concept come back later when we talk about shapes, 3D. So I quickly realized that if I want to put helix around y-axis, then the special thing goes for the y-coordinate. So I would have 3 cosine t, t, and then sine t if the helix wraps around y-axis. If it wraps around x-axis, it will be t, and then cosine, and then sine. So whatever plane had the circle, those dimensions will be populated by sine and cosine. And whatever axis was wrapping around was the one where the t or t squared or whatever the hell equation was that was determining of how fast the helix progresses. Then you put two of these together, you get DNA, right? So there's a lot of cool stuff that you can do with this mathematics. And then you have more examples. You have more examples as you progress. Plenty curve and so on. So that will be the end of this lecture. Now, in your textbook, there is also a piece on limits. But then the next section is called Calculus of these curves. And they cover derivative and integral. But we know that limits are also concept of calculus, right? It's chapter 2, the first thing you learn. So what I do is I move the limits together with the lecture where they belong, right? Which is the next section. So I'm going to cut off here, even though there are limits to be covered. And then I'm going to start the next lecture in about, 10 minutes? With the limits first, and then derivatives and integrals of these space curves. So stay tuned and see you in 5, 10 minutes, whatever. Break time.